What's Thursday in Spanish?
Thursday now.
What's Thursday in Spanish?
Jueves. Jueves. Jueves.
That's what I said, wasn't it?
Thanks, Ed.
Lunes, martes, miércoles, jueves, viernes, sábado, domingo.
Los días la semana son 7.
Hablo español un poquito.
Una mosca es
That's all I know.
All right. Newton's laws. Page 35. I know it says 1.5. It means 1.4. Are we recording now?
Yeah.
Good job, Scott. You just don't get it, do you, Scott? That was from Austin Powers. If you ask people who know a lot about scientists and physics who the smartest person that ever lived was, a lot of them would probably tell you Isaac Newton.
Mr. Willis.
No, none of them would say that. That's because they don't know me very well. But Isaac Newton was amazing. He got so much done at a young age, and yes, he was credited. He's credited with inventing calculus, which, if you've ever taken calculus, you can imagine coming up with it yourself. And he did that in his early 20s. He was a little bit older than you are. And he came up with the laws of motion that we talk about today, and he kind of helped make a lot of sense of the universe. Here's a picture of Newton. I'll turn back to that slide in a minute, if you're wondering what he looked like. His personality, though, he wasn't the best with people. A lot of people didn't like him. He was kind of mean. He didn't...
He's a mean one.
He didn't like when people argued with his theories and such, and he would put you down in a minute. And kind of an interesting character. But his work shed a lot of light on how things move around in the universe. And so we're going to talk about his ideas on gravity in just a minute. It's pretty cool. So, Newton's first law of motion was an object at rest will stay at rest. An object in motion remains in motion. And that's different than what everybody thought at the time. For instance, if you take a ball and you roll it across the floor or down a hallway or outside in the grass, it'll come to a stop, right? It'll roll for a while and slow down and eventually stop. So the idea at the time was, everybody thought that things tended to stop. Things tended toward a state of rest. And Newton didn't say that at all. Newton said, no, an object that's in motion will stay in motion forever unless it is stopped by something. And that was different at the time. And we know that's true. The reason why a ball stops rolling, if you're rolling it across the ground, is because of friction. Friction is stopping it, you see. And Newton kind of came up with this idea that if you had no friction, if there was nothing to stop it, it would go on forever. And that's what happens in outer space. There's nothing up there to stop an object. Very little of anything exists in space. And so an object will just keep on going if it's not acted on by anything. And so if you shoot a rocket off that way, it's going to keep going that way. Pretty much forever. Unless it's pulled or pushed somewhere else by other forces, which we're going to talk about.
Okay, then how do you accelerate when you're in a rocket? Is there nothing to push against?
Yes, if you shoot something out the back, you're going to go this way an equal amount. And that's the segue into Newton's second law, which we're going to look at. Anyway, before I go to that, though, the tendency of a moving object to keep moving, we call that inertia. Objects that are moving have inertia, and that means, and the more inertia they have, the harder it is to get them to change their course. And there are two things involved in inertia: the mass of the object and the acceleration, how fast it's going in one direction. Hey, there's another picture of Newton. There's a stamp with Newton on it. And here we go. This ball, if it's rolled across the table, will keep going straight. Unless it's acted upon by a force, then it'll change directions. That's Newton's first law. And if it's at rest, if it's not moving, it'll stay that way. An object at rest tends to stay at rest. An object of motion tends to stay in motion. It was Newton's third law. That's what you're talking about. Forces act in pairs, which I'll get to. That's the acceleration part. Newton's second law, force equals mass times acceleration. The more massive an object is, the less it will accelerate due to a force. So, if you push on a really massive object, and you can think about this in outer space even, a big satellite that's real heavy is going to be hard to push. You're going to have to get a lot of force just to get it accelerating, to get it moving. But something that's small, a little acceleration will really move it on out there. So mass is important in determining the acceleration of an object from a force. And we can think about that in terms of rockets and stuff. When you're firing off a rocket, if you want to make a rocket that can go real fast, what's a good thing to do with it? What's something you might do if you wanted to take Newton's second law into account? If you wanted to make a rocket that goes real fast, if you want to launch something in space that you can get going real fast with your fuel.
Use the lightest metal possible.
Make it less mass. Use the lightest metal possible. Make it small. What's hard to do is try and launch big things and move them around, because you need a whole lot of energy to do that. So make it small. Newton's third law states that forces always occur in pairs. Any action has an equal and opposite reaction. So this is what Waylon, you're talking about. If I want to move around in space, and I want to go that way, I could take something and push it this way, and then I would go in this direction. And that's exactly what rockets do. They fire up, they have a chemical reaction going on inside them, and an open hole at one end. And so the exhaust from the chemical reaction shoots out that way, and then the rocket is pushed in the other direction. And if you added up everything, it would be equal and opposite. It would be the same amount of force. If you added the force and the mass together, it would be, or the acceleration and the mass together, it would be the same amount going that way as going that way. Same thing happens with a gun. You ever shoot a gun? You shoot a gun, that little bullet zooms off in that direction. There's just as much force going that way. And that's the recoil you feel. And so why don't you go flying that way at 1,000 miles an hour? The bullet goes that way at 1,000 miles an hour.
Because you're a lot bigger than the bullet.
Because you're so big. And you're heavy. And so you only move a little bit this way, and the bullet really flies out that way. Now, if you were going to launch a big, heavy shell in that direction with the gun, and you shot it out at a significant speed that way, you'd go back at a significant speed that way. That's why you see those huge cannons on those ships. They have huge recoil. They fire and they go back. They'll hold this big metal cylinder and goes back. Have you ever seen those things? I mean, you're having it because there's a lot of force going this way, and to get that thing to go that way. Every action has an equal and opposite reaction. So Newton came up with those laws, and they apply to everything, and they apply to space. And Newton also came up with the concept of gravity. And they say that he did this, he thought about this while he was sitting under a tree and an apple fell on his head. Have you ever heard that about Newton? That's probably not the way it happened. That's just kind of an old story. But he's wondering now, everybody knows from Galileo and Kepler and Copernicus, they all know now that planets orbit in ellipses. They orbit the sun, this would be the sun in the middle, and here's a planet, and they orbit in ellipses. But why? Why do they orbit? Why is this planet going around the sun? Nobody knew. They just knew that they did. And Newton was sitting there, and he saw an apple fall, or however it happened, and he thought, well, if the apple falls, and he looked up at the moon, why isn't the moon falling? And he thought about that for a while. Why doesn't the moon fall and hit the earth? The moon's up there, the moon goes around the earth, why wouldn't it fall and hit the earth? And his huge mental leap that no one else had ever made before him was, the moon is falling. That's what is happening. That's why the moon is orbiting the earth. The moon is falling. But the moon already has a velocity to it. So think about this. I want you to think about, where's my globe? Okay. Think about a person standing on the globe. You're standing here on St. Thomas, and you get a gun. Let's say we're standing on a big tall mountain, even though mountains that tall don't exist. And you're going to fire a gun, okay? Of course, if I fire a gun, the bullet's going to take off, but is gravity going to affect that bullet at all? It is. As a matter of fact, if you ask a sniper, they know exactly, because they've trained, if this thing's a certain amount of meters away or a certain amount of feet away, it's going to fall a certain amount, because they know the speed the bullet goes. And they take that into account in their little scopes, and they turn it up a little bit. So they shoot a little above their target to account for gravity, even with a bullet. Did you know this, Sam? You seem to be sleeping. I'm talking about killing people up here. It's exciting stuff. And so, if you fire a bullet, it's going to go, but it's going to fall, and it's going to eventually hit the ground, right? Imagine you're on a giant platform, and you fire a bullet. It'll shoot off, and it'll come down and eventually hit the ground. But what if the gun was so powerful that you shoot it, and it just goes off into outer space? It might be pulled down toward the earth a little by gravity, but then it just goes on. Could you imagine that? That's what our rockets are. When we launch a rocket into outer space, it's just going so fast that it doesn't come back down. It just keeps going, and it gets into outer space. And if we shoot it fast enough off the earth, it'll just go forever. It'll never come back to the earth. Now imagine this. Imagine we shoot it at just the right speed, where you fire it, and it starts falling toward the earth. But it's going fast enough that it goes around the earth. It never hits the earth, you see? Can you imagine that? I mean, when you shoot something, it falls in a curved pattern, right? Well, imagine the earth were right here. Imagine this was the earth. And something came flying past the earth and started falling toward the earth. But it missed it. It never hits it. Well, right here it's still drawn toward the earth by gravity, right? And so it's going to keep curving toward the earth, but it's never going to hit it. If it's going just the right speed, it'll keep curving toward the Earth, but it'll never hit it. That's what an object in orbit is doing. Objects in orbit are going at just the right speed where they curve, where they fall toward the Earth, but they never hit it. They continually fall around the Earth. Does that make sense? That's why you have that feeling, that's why you see people in outer space, they're just floating along in the spacecraft. It's not because there's no gravity up there. There's gravity. Their spacecraft is just above the Earth, probably about this far. They're only a few hundred miles up. But their craft is moving, you see, and falling. They're continually falling. So they're floating inside the craft just like they were falling. Because the craft is falling. It's falling toward the Earth, but it's going fast enough where it misses the Earth. And it falls around the Earth, and it'll continually do that forever. That's what the moon is doing. It's falling toward the Earth, but it's also moving in a direction, and it just never hits it. That's an orbit. And Newton came up with that. Isn't that cool? It's the coolest thing I've ever seen, man. Most people think there's no gravity out there in space where the astronauts are. That's not true at all. There's gravity. They're being pulled down. They're just falling. It's like falling. Imagine you're in an elevator and the cable breaks and the elevator starts falling. You'd be floating inside the elevator. And you could kind of float around and push off the walls until it hits the ground. Then you go plowing into the bottom of the elevator. Die. That would be your last thing, floating inside the elevator.
What if you jump before you landed?
Oh, you'd still hit really hard.
Actually, I think they're on the coasters, you break both your legs, but you would live.
You'd smash into the bottom of the elevator because you're moving.
Like go up into the rest of your leg. Oh no.
When this elevator's going down, it depends how fast the elevator's falling. But if the elevator's falling fast, even if you jump up, you're going to be going down. You can't jump up as fast as the elevator's falling down. So, you die. Isn't that cool? Yeah. And so Newton came up with this idea that gravity is what's causing the orbits. And he's right. The planets orbit the sun. The sun has a lot of gravity. And all the planets are just falling around the sun. And each planet itself also has gravity. So moons can orbit planets. And we can't really feel the gravity of the sun because the sun's so far away and we're on the Earth and the Earth has its own gravity. So we're pulled more by the Earth's gravity than we are by the sun's gravity. So here on Earth, we just feel the gravity of the Earth. But there is gravity of the sun out there too. And it's pulling the entire Earth toward it. And the Earth is just falling around that sun. And has been doing so for 4.5 billion years. So let's talk about gravity. Gravity is a continuous force. Everything that has mass has some gravity to it. You would have gravity to your body. And if you were all alone in outer space, just floating around in outer space, and there was nothing else around you, your body would have a little gravity, and if you released a little object like a BB, it would slowly start coming towards you if you're the only object around. And it would eventually land on you.
But why won't it orbit on me?
Well, it would orbit if you pushed it around. If you pushed it sideways, it would start falling towards you, and it would start orbiting around you. Yeah. Isn't that cool? But you're not alone in outer space. You never will be. There'll always be something else around. Gravity follows what's called an inverse square law. Twice the distance equals 1/4 the force. So gravity is like magnetism. The further you get away from something, like if you get twice as far from an object, the gravity is not half of what it was. It was 1/4. It's 1/4 of what it was. It's a lot smaller. Here we go. Guy throws a ball up in the air. Whoop, it comes back, right? Why?
Gravity.
The Earth has gravity, and it's going to pull on the ball. What Newton's laws tell us is that the ball is also pulling on the Earth. If you throw the ball up, the Earth pulls on the ball, but the ball is also pulling up on the Earth. Every action has an equal and opposite reaction. So why doesn't the entire Earth go up toward the ball much?
It doesn't have that much gravity.
Because the Earth is so massive that it's hard to move the whole Earth. When you throw a ball up in the air, the Earth does move a little bit toward the ball. But it's such a minute amount, it's immeasurable. It's essentially nothing. But if you think about this in terms of two planets orbiting one another, if you have a heavy planet and a light planet, you know, if a massive object comes near a lighter object, let's say we have a small body and a large body going around and they pass one another, they're going to pull on one another. So the small body will slightly affect the large body, and the large body will greatly affect the small body. There will be some change in movement.
Rockets work because of the third law of motion established by Isaac Newton. That law states that for every action, there is an opposite and equal reaction. Inside the rocket's combustion area, fuel rushes out the opening, while an opposite force pushes the rocket forward. In the 1920s,
What is happening?
Robert experimenting with rockets.
Why is it doing that?
Can I get in the bathroom?
No. Wait just a second. Hold on. Oh, this is kind of cool. This is an astronaut who's got a feather and a piece of metal. And he's going to drop them on the moon. And there's no air on the moon, you see? So guess what happens? Have you ever seen this?
Yes. They explode.
No, they don't explode. I don't know what he's holding there. A wrench or something?
You hear about Neil Armstrong?
Yeah. He's got a feather in his left hand. That's a feather.
It's not very good at it.
They land at the same time. So a feather would fall just as fast as anything else if there was no air there holding the feather up. That's a pretty cool thing. Here, at the Vomit Comet, that's the one I wanted to show you.
Oh, I love this.
You ever heard of that?
Yes.
The way they train astronauts to get a zero gravity, feel for zero gravity, is they go up in a plane. They call the plane the Vomit Comet. McLean, you getting this? And the plane goes up like this and then just falls. And the people are inside the plane. And so the plane is falling and the people are falling inside the plane. And once it gets close to Earth, it has to come back up and they all fall back to the ground. And they just do that over and over. And it gives you a sense of weightlessness for a long period of time, you know, a few minutes. And it makes a lot of people throw up. So they call it the Vomit Comet.
Does it show them throwing up?
If you can't handle it, they don't let you become an astronaut. Martian G right there. See, the plane can fall at different speeds. So if it's just slightly falling, you'll have some gravity, but not as much as on Earth. And if it's falling quickly, you can have no gravity. So they can simulate gravity on different planets. Do outer space? What?
I mean, if someone's driving it, right? He's obviously pretty good at it.
Yeah.
At handling it. As long as they tell him to go to outer space.
Oh. I don't know. Maybe they did. Maybe they need more than just one guy. Another thing that they are building right now in Italy that you're going to be able to ride if you want to is a roller coaster that's unlike any roller coaster that's ever been built. It has a car, and the track goes like this, and you take off in the car this way, you get in it, it's like a roller coaster, and you get in it, and they shoot you off this way, and it's going to go up, but it's going to go up really, really, really high. And then it just falls backwards. Oh. And the fall is supposed to be like 18 seconds, which is longer than any fall that you've ever done on a roller coaster. It's like 3 times as long as anyone that's ever been built. And they're going to use it for training astronauts because it's way cheaper than running that Vomit Comet around. And so, and people will be able to ride it, just your regular Joe will be able to pay and ride it. Isn't that cool? And so that thing's being built right now, but it's supposed to go way up. So they shoot you up, and then for about 15 seconds, something like that, you're fine. And then it comes back down.
But how do you feel if you're restrained? Like, I know you can feel it, like, in your gut.
You'll feel your
Oh,
stomach
I
drop.
don't like that.
And they have rides like that now. The free fall at Six Flags, if you've ever been on that, is that. It's the same thing. And what that is, it's just an elevator that takes you up and puts you over the edge and then drops you. And you fall for about 2 seconds, 3 seconds. And then the car comes like that, and then it falls back down and goes under and go up again.
Why does your stomach feel like that when that happens?
I guess that's just the sensation of being weightlessness. It's a
Do you have that constantly when you're in space?
yes, but you get used to it.
Oh, God.
hmm You have that constantly, but your body will get used to it. That's what they do in the Vomit Comet. They
Why
start
does
to
it
get
stop
used
when
to
you
it.
tense your muscles then? Is it just because everything's held in place?
I guess so. I don't know.
That's what I've heard. If you tense your...
So you can think of gravity as being a pull that keeps the planet from flying off into outer space. If you got rid of the gravity, the planet would continue on in a straight line on a path just straight in the area it was traveling. But if you have gravity pulling on it, it curves it. And so there's always a pull of gravity going inward that pulls it on around. And that's what forms the elliptical orbit.
When, like NASA takes off into space, wouldn't it create, I mean, is it strong enough to create like a different force on Earth? Like, would it make it spin faster?
No, well, it would. It does to just the tiniest amount. But the gravity of the Earth, I mean, the mass of the Earth is so huge, and the mass of a spacecraft is so small that it just becomes negligible. I mean, you think about the rocket is pushing this way, it would push the Earth a little bit, but the Earth is so big that it's just nothing. There's hardly any effect.
What about like an atomic bomb?
Even that
That-
is compared to the mass of the Earth is almost nothing. Yeah, the atomic bomb blows up, pushes material upward. It would push the Earth this way some, but it's just so little compared to the mass of the Earth. The Earth is just so large and so massive that just doesn't affect it much. Doesn't move it much, but it does a little bit, a microscopic amount, 0.00000 whatever. The Earth has been moved a little bit. So, here's one last thing. We think about, here's a planet, and when a planet goes around the sun, the planet actually pulls on the sun a little bit. It pulls on the sun a little bit. So the sun is actually going like this, just a little bit. There's a small amount of motion of the sun as the planet goes around it. And we call that a wobble. And we're going to use that. That's a way to detect if there's planets around other stars, if the star is wobbling.